Really. We're going to go from some talks about fire and other stuff to something on the other end of the spectrum. So I'm going to pass the baton to one of my co-PIs, Josh West. There are two Joshes on this team. He's the taller, better looking, smarter one. Josh West is a professor at USC, works on geochemistry as well as landscapes writ large, and has been expanding his intellectual portfolio at an amazing pace. It's hard keeping up with him. And thanks, Josh, for being here to pull together the Cryosphere world. And go for it. Take over. Thanks.
Well, thank you, Josh R. I'm going to share my screen and just provide a brief intro, hopefully, to get us sort of whet our appetite for thinking about cryosphere hazards. And first, I want to thank all the speakers who've talked in the previous 3 sessions. It's been really wide-ranging and very stimulating. And I hope that in this final session, which I appreciate so many people sticking around for, we can extend our thinking up to the snowy and icy parts of the world, motivated really by the fact that there are so many different land surface hazards that occur in areas covered by snow and ice, and they range from debris flows, and we've heard about post-fire debris flows, but of course there's a range of debris flows triggered in snowy and icy environments, to really dramatic features that are unique to these landscapes, like glacial lake outburst floods and thermokarst slumps and failures. And of course, these pose threats to infrastructure and to people around the world. And so just to make sure that we're all on the same page, this isn't just something that happens in the Arctic. Of course, it does happen in the Arctic, and as the Arctic warms more quickly than much of the rest of the world, these kinds of hazards are a particular threat in those regions. But cryosphere hazards are spread out across the world, as this review paper, I think, nicely illustrated, pretty much on every continent globally. And they take all kinds of different forms. So I thought this was really interesting news piece podcast that was on the NPR website a couple weeks ago, April 19th, about glacial lake outburst floods. I encourage you all to listen to it if you want a sort of newsy take on this. It's a really, really fun example. Don't listen to it while our speakers are talking, but maybe look it up after the session. But there's other hazards too. So glacial lake outburst floods are very dramatic, but there's a lot of damage and hazard that sort of is emerging at a much more gradual pace as permafrost thaws and land subsides, and we see slumps like the slump that's illustrated in this nice review paper from last year. And this leads to building damage, infrastructure damage to roads, pipelines, and so on. And then there's a whole nother area in which the thawing permafrost may affect regional hazards, especially in the Arctic, but also elsewhere. And that has to do with riverbank erosion. So this is just a screenshot I put up because this was a video posted yesterday as ice was breaking up on the Tanana River in the Yukon Basin in Alaska, where the ice breakup was undermining the riverbanks and undermining structures like this. So range of different hazards to think about in this kind of environment where climate change meets the land surface. And we have a great set of speakers who are going to tell us about these today, beginning with the kind of glacier setting. And Rowan's going to talk to us, and then talking about some of those ground instabilities, especially in Alaska, from Jaakko Putkonen and Bill Yu, and ending with that case of riverbank erosion that Madison Douglas is going to talk to us about. So really looking forward to these. Thank you in advance to the speakers. And I'll just say, for those who've been here for the other sessions, these will be a reminder, but for those who are just joining, we have a sort of set of questions that we're hoping to get all of your thoughts on as we listen to these presentations. And the Q&A will take place at the end. So hold your questions, or even better, put them into the Google Doc that you're going to find in the chat. And as a final reminder, the session will be recorded. So without further ado, let me pass the floor over to Anne Rowan, who is a associate professor at the University of Bergen in Norway, and who's going to talk to us about the glaciers in the Himalaya. So looking forward to it, and thank you for being here. And I know it's an evening
Thanks,
for you,
Josh.
but appreciate it.
Yeah, it is, but it's still sunny in Norway as always. Okay, thank you. I will start talking. I'm going to talk about the work we've been doing looking at rapid glacier change in the Everest region of Nepal. There's been a lot of field data collection alongside that, but I'm going to specifically talk about the numerical modeling we've been using to try and predict glacier change. So it's glacier modeling rather than hazard modeling, but these glaciers, relative, a range of hazards develop alongside them and cause them to change as well. So I hope we can change my slides. Yep. So the key thing is that when we think about mountain glaciers, we often think about sort of clean white ice. We see a lot of photos of polar ice sheets, polar glaciers, but in the Everest region of Nepal, a large amount of glacier ice is covered with thick rock debris. And this, so this is sediment that's fallen onto the glacier or being exhumed from within the ice. And it significantly affects how the glacier changes and how its geomorphology, its surface processes. And it promotes the development of some of these hazardous landforms that we wouldn't see otherwise. So this is a schematic example showing how when the glaciers, this is a photo of Khumbu Glacier, which is I'm going to talk about, because this has been our field site for the last 8 years or so. And you can see this is the tongue of the glacier. So this is about 9 kilometers long, and it's entirely covered with thick rock debris. But in between, you can see these ice cliffs starting to develop. And this figure just shows that the key thing that is that these glaciers lose mass by surface lowering. So this was the Little Ice Age surface of the glacier, which you can see from these moraines. And then it's lowered down to here, but it's still glacier ice all the way to the terminus, the Little Ice Age terminus. So they lose mass by surface lowering rather than terminus recession. And that's what you see here. So when in the schematic diagram, when the glacier is in balance with climate or relatively healthy, ice keeps flowing through it and debris is exported. But when the mass balance becomes negative, as the climate warms, the debris accumulates across glacier surface and the surface lowers, and then you start forming ponds and potentially ice contact lakes, which, as Josh mentioned, can become the hazards when they, if they flood, if they cause flooding. So I just wanted to, I put in this slide just to identify a couple of slides to identify some of the hazards we're interested in. Drought is a regional and long-term hazard, because glaciers, even in the monsoon-influenced Himalaya, melt before the rains start, and so they're an important part of the seasonal hydrological budget. But I won't spend ages on this, otherwise I won't have time for anything else. There's local scale hazards that this is work by 2 PhD students in our group looking at how the developments of a rough glacier surface, so by the formation of ice cliffs and superglacial ponds, makes them difficult as a mountaineering challenge for people trying to access the mountains in this region. It's a very busy region for climbers, and the glacier surfaces are becoming more dangerous to cross. And then the hazards that maybe most people are aware of is the formation of water, of lakes and ponds on the glacier surface and in front of the glacier when it becomes dammed by ice-cored moraine, which is fairly unstable. And these photos on the left show some examples of these ice cliffs, and there are people circled for scale. Some of them are really huge. And some work we did trying to measure the ponds. So these sort of features affects the mass balance of the glacier, and this is what we've tried to incorporate into modeling. So the model we've been using is a higher order ice-dynamical glacier evolution model created by David Eggum from Aarhus University in Denmark. And we started working together in at the same time as we started in this fieldwork to develop this model. It's a finite volume ice flow model to incorporate these debris feedbacks and see how that would improve projections of glacier change. And the key picture here is at the bottom, which shows how the model evolves. It transports debris through the glacier ice, and that evolves as the glacier evolves. So we catch that feedback whereby thickening debris layers reduce ablation and change glacier evolution. And then we tried to think about how to parameterize the effect of ice cliffs and superglacial ponds into the glacier model, because this figure on the left shows measured glacier surface elevation change from satellite DEMs of difference. And you can see that the most mass loss in recent years is occurring in the middle part of the glacier. And so we were thinking about whether this could be due to the development of these features across the glacier surface. So while there's a lot of work being done to measure them, included by our group, but other groups, to measure the development of ponds and ice cliffs and think about how to model them as individual features, we wanted to find a way to represent this in a glacier evolution model over longer timescales. And that's much more poorly understood, I think. So we parameterized it into a relationship between debris thickness and melt that included the effect of these features based on these sort of parameterization developed from these sort of satellite data to see if we could reproduce this trend. And in the next slide, I'll show you figures taken along this red long profile through the glacier, where we try and compare our model results with these data. So there's a lot going on this slide, but it's showing simulations of Khumbu Glacier using the Ice-dynamical model when it has a continuous debris layer. So when it's a healthier debris covered glacier as it might have been at the beginning of the 20th century. And then with a discontinuous debris layer that includes all these ice cliffs and superglacial ponds. And the key difference is down here when we look at comparing these lines, different lines, colored lines show so the change in surface elevation of the glacier compared to observations, which is the black dashed line for two different time periods. And this is better represented when we include these differential ablation processes, but not completely. There's still a difference. There's still an underrepresentation of ablation. So we thought about why that was, of mass loss. And the other process we identify through the modeling and we see in the field is these tipping points whereby the glacier detaches from the debris covered tongue. The active ice flow detaches and just sort of stops bringing ice down to the lower part of the glacier, which means it can very rapidly become a sort of destable ice and water body. Whoa, too far. And we actually see this physical detachment. You can see some glaciers here where they've cut off and left behind a debris covered tongue. So in the last few seconds, this is my last slide, but just to show you the model outputs from the different simulations with different parameterizations. And I will stop there. Thank you.
Fantastic, thank you, and really interesting stuff. As I mentioned in the intro, we'll save questions for the end. Please don't hesitate to start putting questions and comments into the Google Doc. But for the moment, I want to move on to our next speaker, who is Jaakko Putkonen from the University of North Dakota, an associate professor in geology and geological engineering, who's worked in high mountain and Arctic environments for decades, and he'll talk to us about ground stability in Alaska. So thank you for being here and look forward to your presentation.
Yeah, are you seeing anything?
We are just seeing your Windows background at the moment.
Oh,
slides.
Let me try again. So let's do this. Good.
Same for the moment. I could see your mouse for a second, but for the most part, just the background.
Yeah, I'm not sure what's okay.
Ah, there it is.
All right. Okay. So yeah, thank you for the opportunity. And hey, everybody. I want to tell you today about our new research that we're working here in North Dakota. And this has to do with the predicting the changes in the permafrost and the related ground subsidence in the future. And I don't see the clock. Oh, now I see it there. All right. So why should anybody care about this stuff? Well, in the Alaska, about 80% of the ground is underlined by permafrost, and over 60% of this permafrost contains excess ice. So what do I mean by excess ice? So exercise is something that is not just the interstitial ice that is between the grains, but it's something that actually creates ice lenses in the soil. So now you can imagine if this ice melts, you will have a basically lowering of the ground surface. And any infrastructure or anything you have on that surface is obviously going to suffer from those kind of changes. And then obviously trying to understand this in the future is then critical for all the planning purposes or whatnot. So the overall goals of this project are to develop a permafrost landscape predictive model. So basically try to understand what's going to happen with the permafrost into the future, and not just the temperature, but the effects of the subsidence or the ground disturbance. So how we do this, the goal is to pull all the open source data that is available, any kinds of maps or whatnot, or and then do forecasting in the permafrost thaw, and then combine then the information to then come out with the terrain change and maneuverability estimates for the future. So what methods we use? We are, like I said, going to use the existing data as much as that is available, like permafrost maps and soil temperature data from various locations. We also do field work, and we want to look for near surface soil ice content and thickness of the organic layers, soil thermal properties, and then also what is the current soil thermal regime. So what are the temperatures in the soil, so that we can start understanding and then start building a model how those might change into the future, and how this may then convert into the changes in the landscape and the physical changes. So where are we today? Like I said, we are currently working on this and in fairly early stages, but currently where we are, we're collecting these different kinds of existing data. Here is an example of a ground ice. This is an older map, but it's this estimate of the ground ice, various parts of the Alaska. We have ecotype maps, which is basically describing the vegetation in the ground, and soil characteristics maps, which are then describing the underground material, basically the texture and the grain sizes and so forth. And then obviously all the existing temperature data that is available. And we're currently planning the field sites and the instrumentation. So just to show some illustrations here, what we are currently working here is, you see the map here, and the background color here is this weird beige color, but that's basically just background color. But all the colors, the actual other colors that you see in this map, those are sites that have over 40% excess ice. So these are highly vulnerable to any disturbance into the future. And then we are combining this. We eventually have gotten all this into a GIS platform where we can then combine these information. And here we are looking at the different kinds of soil types that are related to those high ice content soils. Here is an example of a ecotype map. And this is actually highlighting some of the challenges in this project. When you look at this map, it has a whole lot of granularity in it. And obviously, Alaska is a humongous place. We cannot go to every site. We cannot study every site in the field. So the challenge here lies into keeping the product granular enough so that it's meaningful to any end user, but broad enough so that we can actually tackle the problem at some reasonable time and level. And this is where we are kind of, trying to find the right balance and combinations of the information that we combine. So what we expect to get out of this is basically a forecast model that will give us the ground subsidence or disturbance, if you will, in all or most of Alaska in the 2030 or so forth into the future. Now, of course, there is another wrinkle in this modeling, that once we start looking so far into the future, the vegetation is not going to stay stable. It's going to also evolve through time as the climate is changing. The other thing is, that really nice talk about the forest fires. We know from other research that in the Arctic, the forest fires have been increasing exponentially, and I can clearly see that this will also be a major player in Alaska as well. That's about all that I have to say about it.
Wonderful. Thank you, Jaakko. Really nice ending point connecting to fires. So maybe a good place for a question to line up later on in the discussion. But again, we're going to hold discussion for after the presentations. So I'm pleased to shift gears then and introduce our next speaker, who's going to be Bill Yu, and we'll continue talking to us, I think, about ground stability in Alaska. So looking forward to it.
Hello.
We see your screen, but not in presentation mode at the moment.
Okay. Thank me. This. Strange. Sorry. Let me. So strange. Sorry.
Right.
Somehow when show me screen, this button, full screen button disappeared.
Oh, you may be able to go up to slideshow in the menu at the top. That's sometimes another way to.
Okay.
Or is that right? Yeah.
Okay.
Yeah.
Okay. Sorry about it.
No problem.
Okay. Thanks, Josh, for the introduction. So I try to introduce from the engineering perspective. So essentially, everybody know like 50% of land, the North Hemisphere is covered with seasonal permafrost. So they definitely trigger a lot of natural hazard related issue. The engineering aspects also have a big influence on the infrastructure for the safety and durability through the freezing thawing cycles. So for example, like in one example of the infrastructure, like a water supply system in the cold region, this is kind of case in Cleveland, which is not extremely cold. So instead of have a lot of water main breaks associated with cold winter season. Oh, sorry, I don't know why it's moving so fast. Sorry. So essentially, I
wonder if there's an automatic timer that's, yeah.
So essentially, to understand, wow.
Don't worry,
Sorry.
take a moment to try to get it so that it stops doing that.
I didn't say any.
Yeah, get rid of the use timings. Right, exactly. Okay. Great.
So essentially, to understand, essentially the effect of freezing on the ground response is kind of coupled multi-physical process with thermal hydromechanical process, highly nonlinear, and also very important challenge is how to define parameters from engineering perspective. So from sorry, maybe I just use this one step one by one instead. So hopefully it can. So essentially, we have been looking into how to determine parameter-enabled simulations using conventional equipment and procedures. For example, like in civil engineering, geotech engineering in general, like we have been using saturated soil mechanics. We try to involve into unsaturated soil, which is there's a lot of barriers because it's hard to determine the parameters. So essentially, simulation potentially provide a way to leverage conventional testing method to determine the parameters that, like in the unsaturated frozen soil domain, there's a lot of holistic simulation to be implemented. So that's a generic idea we try to explore. So essentially, what we saw is like to understand the microstructure. For example, this example, like soil is constituted of different phases, air, water, and solid. Each of them can be uniquely satisfy a governing equation for transport phenomena. In this case, hydraulic properties. So what we resort to is we try to essentially code the phases in the soil so that we can represent the microstructure. It's like a material concept in general. And then for each phase, then we can focus on understanding to the individual phases, the transport phenomena that liquid, either fluid or thermal transport phenomena in the individual phase, in water, solid, or air. So with that concept, then we developed this like a random finite element model schema. So essentially, we encode the phase in the soil into different phase field, like a model. Then we focus on understanding the behavior for individual phase and put them together in a unique, like according to the soil features. So essentially, this is like artificially generated soil structure model. You have aggregate, air phase, and liquid water. All these things represented. So for example, like this then allow to simulate. So we define a governing equation which just still conform to generally like a physics law. So essentially, we define this one on the individual phases, like solid, air, or liquid phases, water phases. So this then what it can do is when in a conventional finite element model, we would simulate in a transport phenomena in water flow, we will have equipotent line, like perpendicular direction flow. But when we consider different phase distribution, we not necessarily get the exact perfect equipotent line. Actually, they show zigzag shape according to the microstructure. So essentially, like this is them like a flow line. So in the flow line, it's not a straight line like in soil mechanics. It's we typically tell it's a straight flow line, but in the reality, it's not decided by the microstructure. So with the phase run finite element model, then we can actually predict the water flow in a zigzag pattern for a different type of soil according to the microstructure. But that will give us equivalent hydraulic properties that we commonly use and we commonly measure and utilize in the simulation. So this essentially with this concept, what we can do is use a random finite element simulation combined with a conventional procedure, like a test of soil in a complete saturated condition or complete dry condition. Essentially, from our study, we say we should be able to predict for example, unsaturated hydraulic properties and the soil water characteristic curve directly from simulation, integration, conventional experiments, and random finite element simulation. So that provides a way to determine the nonlinear complex parameters required for holistic simulations. So the other domain, like if we extend the concept to more field, like thermal field, like for frozen soil, essentially we start from set up pretty control experiments as well model for the model validation. So essentially with the similar consider microstructure into multi-physics simulation, we can simulate the temperature process pretty holistically and compare pretty reasonably well with experimental measurement. And then so the other thing is like because for infrastructure domain, the internal stress production is very important for the durability with many material breakdown because the internal stress, because when water flows into ice. So essentially with this random finite element model, this again is conceptually, we can simulate different phases and phase transition. And because we can essentially consider the water phase volume expansion when the transition to ice, then which then leads to like when the freezing thawing happens, we can simulate determine the hydraulic process as well as like thermal process and the internal stress production. So instead, this is just a scheme, like a illustration because with this phase distribution, essentially we allow it to holistically simulate all the phenomena from fundamental physics. If we then this simulation framework to see what climate effects on the cold regions like a slope. So essentially, in this example, like select one location in Alaska, like historical climate data, and using future climate model can predict future climate condition. So this is essentially say like with the different climate prediction scenario, in general, the weather, like temperatures rising up. So this is there's like a constantly like every some years. So essentially, the historical maybe close to present and in the future how the climate will look like from the like accepted climate model. If we then introduce that one to simulate landslide, so what we introduce is for example traditionally, so essentially that one require to determine the failure condition which is related to the strength of soil, and then particularly for the soil in the unsaturated, like a partially frozen soiling condition is kind of challenging. So we introduce is like a localized factor of safety concept. Use localized stress condition compared with the strength parameter, but so that allows to determine factor of safety. But then the important issue is the strength of soil changes because of the degree of freezing or thawing. So essentially, the random finite element model we brought essentially allow to predict, estimate the soil strength parameters and the different extent of freezing thawing condition. Because we can run digital simulation of a digital sample and to find out the strength behaviors. So instead, this is an example, like with a random finite element model consider phase distribution for frozen soil, definitely have higher cohesion, equilibrium cohesion versus unfrozen soil. Instead of we can simulate the more like failure stress and the stress condition and the failure condition coordinate the soil at a different extent of freezing and different extent of saturation condition. So then that allows to determine strength parameter, which is required for landslide analysis. In the traditional landslide analysis, we essentially using traditional circular sliding models that would give us a different sliding behaviors. And also when the different swing thawing extends, the factor of safety kind of changes. So from complete frozen permafrost slope, it kind of relatively safe. With more thawing happens, the factor of safety decreases until to a certain extent start to fail. This will be the result from the conventional landslide analysis we use in civil engineering. And then maybe more holistic ways to direct simulate heat transport. So essentially say example, consider the climate process input to the slope, the permafrost slope, and then with the thawing, essentially the thermal field will change, but it's not uniform distribution. And then allow to determine the extent of landslide distribution. This one essentially plot a counterplot for the factor of safety, localized factor of safety at different months. So essentially at some season we have more slump failure at the surface, which is correspond to a factor of safety less than 1. So if we compare the climate effect, so essentially with the climate change as an input, for the different weather input, essentially we see a more larger range of landslides happening along permafrost slope. Compared with baseline.
We need to ask you to wrap up, Bill.
Okay, sorry. Yeah. So essentially, a forest fire, if the fire process goes on, essentially, so just definitely have an influence on the shallow depth landslides from the heat, some transport perspective. So also study the other one. So in the end, I'm trying to say, from engineering aspect, definitely climate play important role in cold region environment, geohazard infrastructure. The fundamental, we definitely need a fundamental understanding about it, and also develop new tools and that allow to capture the multi-phase process. And in the engineering perspective, it can provide a very powerful tool. Okay, sorry, yeah, for the same thing going on.
Well, thank you, Bill. Thank you for working through the technical issues, and appreciate your presentation. And it is a nice link to the forest fire in the permafrost region theme. So for the final presentation in this session, we're going to move to Madison Douglas, who is just finishing a PhD at the California Institute of Technology and is going to be talking about riverbank erosion in permafrost terrain. You're muted, Madison. But we can see your slides, so that's good.
Okay, great. Can't have everything be completely perfect. But yeah, thank you for that introduction, Josh. So I'm going to be talking about how sediment entrainment can limit permafrost riverbank erosion. And this work was done with some of my collaborators, Kieran Dunn and Michael Lamb. And in the background of my title slide, you can actually see a photo motivating why we should study riverbank erosion. You can see some power lines and some pipes that are extending from the bank. And that's actually where home used to be. This is on the edge of the Koyukuk River. And so for people who live along rivers in permafrost regions, bank erosion rates have a very immediate effect on their lives and livelihoods. And let's see. Before I get started, I just want to thank the ancestral and present day Koyukon Athabaskan and Gwich'in people living in Huslia and Beaver, as well as the Huslia and Beaver tribal councils for their care of the land where I did fieldwork throughout my PhD, and that motivated a lot of this research. And so just to take a step back and give a broad overview of some of the dynamics of Arctic rivers, there are very large river systems that flow through permafrost regions. On the left, you can see a top-down view of many of the largest watersheds. And in general, due to polar amplification of climate change, these rivers are already responding to changes in the climate by increasing their discharge and increases in river temperature on decadal timescales. And so I wanted to understand how these changes in discharge and temperature might affect bank erosion rates. And again, just to kind of motivate this in the context of hazard cascades, in addition to actually threatening the homes of people who live there, there are hundreds of communities throughout the Arctic located on riverbanks. On the right side, you can see a news article from NPR with an example of the village of Newtok, but many other places are also at danger due to the release of pollutants, specifically mercury and permafrost, and then also landfill materials that will be eroded into the river. Changes in river temperature and turbidity, with turbidity being increased potentially by bank erosion events, can affect fisheries, which is extremely important for people who are subsistence fishermen as their livelihood. And finally, riverbank erosion can release organic carbon into river systems, which may then be oxidized into greenhouse gases such as CO2 and methane. And this could provide a positive feedback on climate change, enhancing all of the hazards that we've seen discussed throughout this session. So with that context, the easiest way to try to understand the effects of climate change on bank erosion rates would actually be to just go out and measure them. And on the left here, you can see some model results from Joel Rowland et al., where they tried to measure decadal scale riverbank erosion and accretion rates on the Yukon River. But there's significant spatial and temporal variability in erosion rates. Here they have a plot of the rate of bank change versus distance downstream. And you can see that many effects, including river curvature and the bank material properties, affect erosion and accretion rates. And so that motivated me to try to develop a theory for bank erosion rates that could help us determine hazards at specific locations. And so to do that, we investigated previously published work in the literature, and in particular, Costard et al. Have done a large amount of experimental and field work on bank erosion. And they usually work off the assumption that permafrost bank erosion rates are thaw limited. So you have to first thaw the bank, and then as soon as you can thaw the bank, the sediment is going to be immediately transported downstream. So in this case, bank thaw rates are limiting how fast you're eroding. And so on the left, I have the equation that they use based on a Stefan solution. Here we have the erosion rate depends on how much heat is required to thaw a unit volume of permafrost. It also depends on the characteristics of river water, such as its specific heat and density, as well as the water velocity, this scales with discharge, and the water temperature, both of which we expect to increase as the climate changes. In addition, we have this heat transfer coefficient out front that tells us how fast this heat is going to be transported between the river and the bank. So what we can do then is plot up these model results for a case study along the Yukon River. Here we have water discharge on the y-axis and water temperature versus days of the year, and with 0 being January 1st. And what we find is if we plot up this model versus the actual measured rates from Rowan et al., this model way over predicts bank erosion rates. It's predicting 10 kilometers of bank erosion rates versus actual observed rates of a couple of meters a year. And so something is off here. At first we thought, well, maybe the heat transfer coefficient is wrong for some reason. And so I did a set of frozen flume experiments, which I won't be presenting here, but we found a different heat transfer coefficient that matched our flume experiments. And even then, we're still predicting erosion rates that are way too high. So instead, we hypothesized that maybe this equation is correct, but it doesn't actually apply all the time during the summer. Maybe there's another physical process that could be limiting bank erosion. And so we hypothesized that bank erosion could be limited by sediment entrainment in addition to permafrost thaw. And so whichever one of these two processes is slower would then provide the limit on bank erosion rates. And I'm just going to walk you through a cartoon hydrograph and thermograph for the river. We have discharge on the top, temperature in the middle, and bank erosion rate on the bottom versus months of the year. And we would expect the entrainment limited bank erosion to scale with discharge more closely than thaw limited bank erosion. And so potentially the minimum of these two curves could produce a slower bank erosion rate than either one independently. And so to do that, we added a new equation to our model, the entrainment and limited erosion rate. And we used the standard kind of excess shear stress version model of Parthenides 1965, where erosion is proportional to some empirical coefficients, the properties of the sediment, its size, specific gravity, and threshold of entrainment, as well as the water depth, which again, we should scale with discharge, and the channel slope. And so if we use these two in combination, we come up with a new model that is capable of producing more realistic erosion rates at a given location than the previous thaw-limited models. So just to kind of take a step back and offer some conclusions from this work, we found that Arctic riverbank erosion is likely limited by permafrost thaw as well as sediment entrainment. And in the thaw-limited erosion regime, erosion rates can be incredibly fast, and they should scale with water temperature. We also found that bank erosion rates should increase for discharge under both conditions, which indicates that there's still a high risk of river pollution, damage to fisheries, and to the lives and livelihoods of communities in the Arctic as these rivers warm and evolve. So thank you very much for your attention, and I'm excited to answer questions in the upcoming Q&A.
Fantastic, Madison. Thank you. And thank you to all of the speakers who've contributed in this session. Really appreciate it. And thank you also to everybody who's in the audience and has stuck through to the end of this morning's well, this morning for me in California, but of today's presentations. I think it's been a fantastic overall picture. We'll spend some time on discussion related to this last session, and then have a few minutes for some wrap-up reflections and discussion at the very end before the top of the hour. So a lot of good questions coming into the Google Doc. Please can keep contributing those. I guess I'm curious, maybe to start off with, and ask a little bit about maybe this is something you touched on, Madison, and others could reflect on it. Somebody's asked about thinking about bidirectional feedbacks between changes to the permafrost landscape and future climate scenarios caused by, for example, increased methane or other greenhouse gas emissions. And I guess maybe I'd be interested to hear some of your thoughts from all of you about the tractability of really linking the kind of land surface change to greenhouse gas production to global climate and evaluating those feedbacks. Is that, is that a doable thing? And what are the possibilities there? Anybody want to jump in and offer a
I'm happy to lead this off. So I think one of the things I've been seeing, just to address the perspective of kind of lowland alluvial river systems, is you have alluvial rivers are really cool because they make the topography of their own floodplain. And so there's been kind of this increasing recognition on the microbial ecology side for permafrost research that places where you see hotspots of methane and organic carbon emission can be linked to features like soil moisture and elevation. And it's interesting that you have this feedback between river morphodynamics and environments that could be really good at either producing methane or storing carbon potentially. And Catherine Lineger's done some excellent work on this as well. And I think in addition, one of the real strengths in trying to monitor carbon effects on the Arctic, the carbon cycling in the Arctic is that in general, most rivers can serve as integrators of what's happening throughout their catchments. And so you can make measurements near the outlet of the river to the Arctic Ocean and try to get a sense of what's happening at this large catchment average scale. But you do have to take into account how those signals are being changed as they're propagated through the river network. So I think there's a lot of really exciting research opportunities to better understand links between carbon cycling and river networks in the Arctic to better monitor what's happening right now.
Any of our other speakers want to chime in on that?
Well, yes. I mean, the release of methane, carbon dioxide, and such from the thawing permafrost has been the topic of research for tens of years already. And people have been flying low flying aircraft and before time of drones, but in any case, and measuring very carefully what and where and how much and what time of the year and so forth. There have been measurements of the thaw lakes, how they are influxing the carbon dioxide in the summer usually. So yes, there definitely is a link. And the other thing is that if the Arctic areas are getting drier, there is a large amount of peat bogs in those areas. And this would, again, if they start drying up, they would start basically decomposing and releasing also CO2. So there are direct links, but then how that propagates back to the excess warming, that's kind of question for atmospheric scientists, how that part works. But definitely there is a link, yes.
Maybe I can ask you to, the four of you to reflect on a different set of questions, which is that you've all talked very nicely about thinking about sort of mechanistic models, process-based models for what's happening in different parts of the cryosphere system, from glacier surfaces to riverbanks. Can you maybe offer some reflections on how what the path is for taking those process-based models and developing hazard assessments? I mean, we've seen in some of the other sessions, for example, earthquake triggered landslide predictions that are sort of global in extent, right, immediately after earthquakes. How far are we from being able to take, a glacial surface evolution model and use that to develop probabilistic assessments of glacial lake outburst floods, or similarly for infrastructure effects across Alaska? Maybe you could give us some sense of where you see that modeling territory.
Well, if I can jump on that, because the project that I'm working on, the sole purpose of the project is to develop tools, sort of accessible tools for end users of the surface disturbance. So that's exactly what we're trying to do here. So therefore, we are not so concerned about creating new research necessarily, but integrating everything that is already out there and putting it into a format where the end users can use it for any purposes, traversing the terrain, building new roads, houses, villages, whatever it might be. But obviously, while we do that, we also want to improve and make sure that the older measurements, they still hold and so forth.
Yeah, I also echo the comments. I think for example, in the geotech engineering community, which we kind of more smaller scale directly related to political engineering project, we have evolved from a probability-based model to risk-based model. So essentially, you consider different variabilities to find out the likelihood of landslide may happen. But beside that one, also from the intervention aspect, maybe we prioritize the the intervention based on the risk assessment that require considering the implication of a failure of engineered slope or natural slope, how much the consequence might cause for the communities. So essentially, that I feel that can be evolved into pretty interdisciplinary perspectives that require to integrate geoscience, geotech engineering, and also communities as well, social science as well.
Yeah, I was just going to say that I agree with that. From the glacial floods point of view, it's we can use estimates of ice thickness to look where there are over deepenings beneath glaciers, and where lake basins might be in the future when the ice is gone. But then you also need to know whether there will be a dam, whether the sort of distribution of relic ice and sediment that might hold water in that basin, and also how the glacier will stay in contact with the lake, because you can, if the front of the glacier calves, that can be a process that can cause a flood. So there's quite a complex set of processes to put together, and I think we're a long way off doing that actually.
Great. Yeah, thank you for those reflections. Maybe I'll add one more question for this group before handing back to Josh R for some to guide us on some sort of synthesis and reflections. And that is just one of the questions that somebody contributed into the Google Doc was whether there's anything to be done to slow the riverbank erosion process if we know it's going to happen. That's obviously a question very specifically for Madison, but maybe the other speakers could also comment about, what are in these kinds of complex terrains, are there interventions that can be made when it comes to permafrost terrain collapse? I don't know.
Yeah, I'm happy to lead that one off. I think one of the things I've learned from doing fieldwork and talking to the people who live in these environments is that they're actually not having infrastructure in some cases, having infrastructure getting eroded and having to move. This isn't like the first time that's happened. People are very well aware that the river migrates around, and in many cases, specifically Huslia, they previously tried to slow down efforts to erode it, and or for the bank to erode, and they're aware that it's going to happen. And some we were at a town meeting type thing, and one person was like, yeah, we'll just make a cutoff, then the river will reroute itself, and then we won't have any bank erosion here. And so I think there are kind of some interesting opportunities for very non-traditional from the engineering side ways of adapting that communities can adapt to living in these environments, or could potentially have engineering solutions. And so I think there's kind of a lot of different aspects of decision making that have to happen, but part of it is just making sure that people who live there are well informed, but then have the agency to do the solution that seems best to them.
Yeah, if I respond to that, it's worth keeping in mind that the vast majority of Alaska is totally uninhabited. So for those reasons, probably there is no need to try to stop the warming of the permafrost. And part of that, in a way, that process, at least, it's a natural process that takes place. But I think that the key part in my mind is that the people who live there would have a better understanding what's coming, so that there could be a preparation, and then obviously planning for future infrastructure or a situation of, I don't know, airports and any major structures and so forth. And then there are some sort of a defense considerations as well for the sort of a national security and so forth.
Great. Well, again, thank you to our speakers in the session. Much appreciated. Really great to have that this focus rounding out our day. I'm going to hand over to Josh R. To guide us in some synthesis. And again, just a big appreciation to everybody for taking part from me.
Thank you.
Thanks, Josh. And I really want to highlight the theme that just came out of the speakers in your session, which is that there's a tremendous demonstration all morning or all wherever you are in the day of why we're doing this, and this tremendous dedication to serving communities. And I think we heard it's impossible to talk about your model without pointing out why, and communities in Alaska and other parts of the world that we've heard about today. The hazard cascade is very real. And I think our community's recognition of that and commitment to doing science that speaks to that is the whole reason we want this center to be successful. And so bringing together this really amazing extravaganza of modeling has been scientifically incredibly inspiring. I've got pages of notes, and we will be working with everyone to keep integrating all this. But I think, ultimately we want to help integrate what we've heard about. And one of those challenges is that I think a lot of us are aware of how our modeling and how our work connects to other forcings, connects to climate and other geologic hazards, but how to make it talk, how to make these different pieces of the system work well together is a big challenge. And so one of the things we want from the community is your ideas on how we can facilitate that. We have plans for a workshop in the fall to get together with people that really want to dig into this kind of stuff and engage in model coupling and understanding how to connect these systems. So we'll be communicating with the group about that and the details of how to get involved. But more generally, if folks want to turn on their camera, unmute yourself, raise your hand, or just sort of speak to anything you saw today that you would love to see some follow up on that we as a Clash Center and we as a Clash team should pay attention to, please do so. You can do that right now in the Zoom, or Jill is posting on Avenue a Google form that you can present some feedback in. Again, we are here to serve you. This is for all of us as a community of geoscience and even beyond, as we've heard about today. Tomorrow, we're going to talk about water, sediment, landslides, and human aspects of hazard cascades through exposure and risk. We know we have to have tendrils that reach into all these disciplines. So we really want to make a plea to you to help us do this well, how to help us be successful. So please use that Google form, or if you have any parting comments in the last minute or two here, we'd love to hear it. But again, thank you to the session coordinators. Thank you to the speakers. We hope to keep seeing all of you in different venues, AGU and elsewhere in the meantime. Any other parting shots before we sign off and let people go on with their day? All right, we've done our Zoom thing. I really can't appreciate you all. Hope to see you all tomorrow. And don't forget about geoclash.org. That's a place that you can find our activities online as well. Thanks again, everyone. Thank you, Jill, Adriana, Noah, and the Clash support team as well. We'll see you all soon. Thanks.
Thanks, everybody.